For the final part of this first lecture, we'll explore ocean salinity in some detail and ask these sorts of questions. Why is the ocean salty? What is the amount and composition of salt in the ocean? Why does the saltiness of the ocean vary from place to place? Where does that salt come from? And how long does that salt remain in the ocean? Or if we're thinking in terms of systems, what is the residence time of salt in the ocean? So what is salinity? Salinity is the amount of dissolved salt in seawater. These salts take the form of ions like sodium, chlorine, magnesium, calcium, sulfate, potassium ions, and these recombine to solid salts when seawater is evaporated. The average seawater contains about 35 grams of salt per kilogram, or 3.5 weight%. We generally measure it by electrical conductivity rather than evaporating the seawater. It's much easier to do. The conductivity is proportional to the amount of salt in the water. We report salinity in units of 35 parts per thousand, or PSU, practical salinity units. You might just notice that this symbol here, which is like percentage, parts per 100, this is parts per mil, where mil means thousands. So this is 35 parts per thousand. If we look at the salinity of the surface ocean, what we see is it varies quite a lot from place to place, between about 30 to 40 practical salinity units. And so we'll have a closer look at why we get this variation in the surface ocean. The French chemist Antoine Lavoisier and his wife Anne-Marie first measured salt in the ocean. Okay, looking at the analysis of water, here we have the concentration in parts per thousand, or grams per kilogram. So water is obviously mainly hydrogen and oxygen, and that's 96.5%. of seawater is made up of water. The other 3.4 weight% is made up mainly of these salts here. But there are also a whole range of other elements in much smaller concentrations. The bulk of these dissolved elements are sodium and chlorine, or sodium chloride or common salt, and they make up about 90% of the total dissolved solid material. This is just another way of looking at those same data. So we have seawater, this is the amount of salt, 34.4 grams per kilogram is salt, and then this just splits it up into those remaining salts, and you can see that sodium chloride makes up the vast bulk of the actual salts. So why does sea surface salinity vary, and why does it vary so much? If we have a look at this diagram of sea surface salinity, I'll point out a few features. Here we have the Mediterranean Sea, and we can see that the salinity is up around 39 PSU or greater. So it's much more saline than most of the rest of the ocean. You'll also notice that there are bands of high salinity that run across the mid-latitudes. And we have lower salinity in general along the equator. And another interesting feature is the very high salinity in the Atlantic Ocean relative to the other oceans, the Pacific and the Indian Ocean. Another feature that you might notice up in these areas here, in the North Pacific, and also in these regions here, as well as the Bay of Bengal. These areas of really low salinity are where the major rivers run into the oceans. Going back to the Mediterranean, the high salinity along the mid-latitudes, and why the Atlantic Ocean is more salty than the Pacific Ocean. So much of this really comes down to what the net evaporation precipitation balance is in the ocean. The mid-latitude zones and the Mediterranean are areas where there's much greater evaporation than precipitation. So there's a net imbalance of fresh water, and in those areas the ocean becomes saltier. And you can see where the precipitation is high along the equator, we have low salinity. So why then is the Atlantic more saline than the Pacific Ocean? So we might think that, oh well, in the Atlantic, there's just simply a lot more evaporation over the ocean than precipitation. But we actually have to think a little further than that. The balance in the Atlantic relative to the other oceans is because there is less precipitation, not only less precipitation over the ocean than evaporation, but we also have to include all the river basins that flow into the Atlantic relative to the river basins that flow into the Pacific and other parts of the ocean. So when we combine those river basins, the net evaporation over those river basins that flow into the Atlantic, and including the ocean as well, we have greater evaporation than precipitation. Another area where we have significant changes in sea surface salinity, we get much higher salinity, and it doesn't show up on this particular map, is where we have sea ice formation at very high latitudes, so around Antarctica and also in the Arctic Ocean. So when we have sea ice formation, what happens is the dissolved salts are rejected from the ice when it's forming. The remaining water has much more salt in it than the water that is frozen. So just returning to this, the question of why the Atlantic is more salty than the Pacific, and noting that there are many large rivers that actually flow into the basin, when you do the total water balance for the Atlantic Ocean and the river basins that flow into it, you find that there's a net transfer of water over into the Pacific and the Indian Ocean basins through the atmosphere. Wally Broker added up these fluxes of water through the atmosphere in different areas and was able to calculate that there were, on average, there were 0.32 spheredrops of water transferred from the Atlantic Ocean basins into the other basins via the atmosphere. So one spheredrop is 1 million cubic metres of water per second. Every 3 seconds, there is a net transfer of 1 million cubic metres of water out of the Atlantic basin over into the other basins onto the land.